Welcome everyone. We will be looking at the notes entitled Angles today, and as a matter of fact this will start our trigonometry unit, and really everything we talk about in this unit revolves around the concept of angles. So today, very simply, we're going to lay the foundation of what an angle is and certain measurements as well over the next couple days. So let's start that process out. It says on your paper sketching an angle. And actually what I'll probably do is define an angle in a slightly different context than what you've seen before. So let's see if we can get that to work. So on your paper it says begin with a horizontal ray. And so everybody, what I'm going to ask you to do is just probably come right over here. And let's go ahead and draw a little vertex if you would. And a horizontal ray kind of like that would do. And so if you want to label some things, not a bad idea at this stage. That's going to be our vertex right there. And then what we're going to do is label this ray the initial side. So put that in place if you get an opportunity. So we start with that, and then here's where the definition of an angle really comes into play. It's this piece right here. And so what we're going to basically do is, if you can envision a second ray sort of right on top of that initial side right here. And what we're going to do is rotate that second ray off of the first ray. And so it's either going to rotate upward like this, or it's going to rotate downward like this. And so for our purposes here, what I'm going to have you do is just kind of rotate a ray this way in what's called a counterclockwise direction. Let me repeat that. Right up like this. And then go ahead and draw a terminal side, and that's exactly what we'll label it right in there. So we have a terminal side, and here's, I guess, the best way to describe it. A terminal side rotating off of an initial side. And so in this particular case, it rotates to right there. And we're going to go ahead and denote our angle. We're going to see this a lot over this unit. It's what's called a theta, sort of that Greek letter. It's like a 0 or an O with a little squiggly right up there. And then one concept that we're going to really refer to during this lesson is how the terminal side rotated off of the initial side. So I do want to include that. And so the way I had described it is that terminal side rotated off of the initial side like this and stopped right there. So if you can kind of draw that in as well, that would be great. And so again, really in terms of our angles today, we're going to really talk a lot about the terminal side rotating off of the initial side. A second ray rotating off of the first ray. And so we're going to talk obviously about different ways to measure those angles. And so it says on your paper, the measure of an angle is based on two characteristics, both of which I think I've alluded to already, but let's get them written down here. Number one is the direction of the rotation. So put that in play if you would. And let me come back to my angle right here. We'll talk about these words just coming up in a little bit, but basically that second ray, I rotated off this direction right here, from here to here. And again, I characterize that as a counterclockwise rotation. Theoretically, everybody, I could also have rotated it this way in more of a clockwise direction. So the direction of the rotation is going to help us determine our measurement. Also, of course, not just the direction, but the amount of the rotation. And that would be the second characteristic that goes into a numerical measurement. So the amount of the rotation. In this case, again, coming back to the angle that I drew, I just went from here to here and stopped. If I went further, it would be a greater angle measurement. If I went shorter, it would be a smaller angle measurement. So those two things, the direction and the amount, go into determining the measurement of any angle. So we're going to talk a lot about angles here, and if you don't mind, can you underline this piece on your paper, what's called the standard position of an angle. And really most of what we do in trig will, again, revolve around this concept right here. All our angles will be in a uniform position, what is called the standard position, and here's how it's defined. The initial side, so now we already know what an initial side is. So the initial side is on the positive x-axis. So right now that implies that we're going to be using a coordinate plane. So the initial side is on the positive x-axis, and the vertex is at the origin. Okay. And so we're going to illustrate this, obviously, in just a sec here, but please make sure you have that piece in place. So the initial side is on the positive x-axis, and the vertex is at the origin. So what I'm going to ask you to do if you get a chance is to give me two coordinate planes, kind of side by side there if you get an opportunity. Just something like this, no tick marks necessary. And we'll jot a few things down in relation to this piece. But basically, let's start with throwing an angle in standard position onto the coordinate plane. So what I'm going to ask you to do, everybody, is just with this first one, please put a vertex right at the origin there. And the initial side, let's run it along that positive x-axis. That would be this piece right here. And again, what we're going to do is rotate that one direction or the other. And you'll hear me say this a lot in this unit, but direction matters in trigonometry. And so let's go ahead and rotate this terminal side off of the initial side, kind of like this. Let's go in that counterclockwise direction again. And if you get an opportunity, just go ahead and throw a terminal side anywhere you'd like. Doesn't have to be up there. But basically what I'm going to do is illustrate this piece. Here's my theta, everybody. And I went counterclockwise from here to here. Sort of a repeat of the way I drew it initially. And what you're going to write for me, of course, is the two pieces. Well, actually, the one piece for right now, and then we'll get into the second piece in just a moment. But this was what we would call a counterclockwise rotation. So please put that on your paper there. And anytime we have a counterclockwise rotation, our angle will be a positive measurement, a positive number. So angle measurement, that's my symbol for angle, by the way. So angle measurement is positive. Okay, so by definition, anytime we rotate that terminal side off the initial side in a counterclockwise direction, we're going to get a positive angle measurement, which obviously implies the second piece. So let's come right over here. And everybody, in the second coordinate plane, if you get an opportunity, let's go ahead and throw a vertex at the origin, please. Initial side along the positive x-axis, kind of like that. Again, just to illustrate that one more time. And in this particular case, everybody, we're going to go ahead and rotate that terminal side off the initial side, but I'm going to come this way around clockwise. And again, just throw a terminal side wherever you'd like. I'm just going to go down here. It's nice and easy for me. And I'm going to put my theta right in there, in between the initial side and terminal side. And very simply, I do need to indicate how it rotated from there to there. That is so vital for what we do today. And so in this particular case, I'm going to indicate that piece right there. I rotated from here, starting with my initial side. The terminal side rotated this direction, this amount, and stopped right there. So that's the terminal side. And again, I think this implication is already in place, but let's write it down. Anytime we have a clockwise rotation, and again, this probably differs from anything you've seen before dealing with angles, but anytime you have a clockwise rotation, the angle measurement, by definition, everybody, is negative. So as I said, in trigonometry, direction matters. I guess the one analogy I sometimes use with this is with like physics, something along those lines. In physics, when you talk about velocity, direction matters. When an object is going upward, its velocity is positive. When an object is coming downward, the velocity is negative. The direction matters, and that positive versus negative indicates the direction. Same thing here with the angles. So a counterclockwise rotation, by definition, the angle is positive, and a clockwise rotation, by definition, the angle is negative. Okay, good. Let's continue forward here. And let's see, it says on your paper, draw a coordinate plane. Again, we'll be working a lot with the coordinate plane over this unit. Draw a coordinate plane and label the 4 quadrants. So just as a reminder, and let's go quadrant 1, remember, starting with x and y being both positive, and then it goes in a counterclockwise rotation there. So this is quadrant 2, this is quadrant 3, and this is going to be quadrant 4. And you definitely need to know those as we move forward with this. Okay, and an angle is named Well, let's go ahead and, well, we're going to dot, dot, dot this basically, but let's fill it in. An angle is named after the quadrant that the terminal side resides in. After the quadrant that, there we go. So you're going to hear me talk a lot about quadrant 2 angles, quadrant 3 angles, quadrant 4 angles, whatever the case may be. And what that means very simply is that is the quadrant that the terminal side is in, either quadrants 1, 2, 3, or 4. If it is on an axis, and students ask this all the time, but if the terminal side is on an axis, which is definitely possible, it has a different type of name, which we'll get to in due time. Okay. Now there are going to be actually 2 units of measurement that we're going to see with angles. The one that you probably are most familiar with would be the degree measurements of angles, so we're going to start out with that. And it really revolves around this initial definition, which we will modify and then utilize, of course. But very simply, one complete rotation counterclockwise, so that means it's going to be positive. So envision that, everybody. Counterclockwise rotation, what would that look like? And if you remember correctly, of course, one full rotation around would be 360 degrees. And which means then we can start talking about degree measurements and fractions of rotation. That means that 1 degree would be 1/360th of a counterclockwise rotation. Excuse my shorthand on that, but I hope that works for you. But that's how we would define 1 degree. It's 1/360th of a rotation around in a counterclockwise direction. So by defining it this way, we're now able to start putting numbers with our directions and our amounts of rotation. So 1 degree is 1/360th of a rotation. If you can kind of envision an angle, specifically that terminal side rotating off the initial side, basically as it rotates all the way around in a full circle, it stops, well, it doesn't necessarily stop, but it hits 360 degree increments as you move around. And so we'll kind of talk about that piece. Is each degree represents 1/360th of a rotation, another increment as you move around a circle. So just different rotations and different degree measurements that you're going to have to be comfortable with. There are some measurements that come up time and time again in this unit, and so we're going to want to work through those purposefully. So let's start it out there. And again, you can start filling some of this table in if you need. You can work ahead of me if you'd like. You can pause the video if you'd like. But what we'll do is just talk about it in terms of half a rotation around. What would the degree measurement be? And what would that look like? I need you to start visualizing these angles. So it's not just number crunching today, but a lot of what we're going to do is visualization. Can you see the angle measurement? If I give you an angle measurement of 90 degrees, can you visualize where that terminal side is? There's a lot of visualization that goes into trigonometry, which we'll work on. Okay, well, let's start that out. If one rotation around is 360 degrees, I'm hoping you all agree that half a rotation would be 180 degrees. So let's fill that in right there. And let's go ahead and just sort of build a sketch, again, if you get an opportunity there. So terminal side, half a rotation would be on the negative x-axis, kind of like this. But here's the thing, everyone. We have to be very, very careful. I do need us to put in how the terminal side rotated. That's 180 degrees right there. What we are going to find is that theoretically there are an infinite number of ways to get from any initial side to its terminal side. So you have to include the rotation in order to show a particular degree measurement. So that is 180 degrees right there. A third of a rotation, so about a third of 360, would be 120 degrees. And think about it as we kind of go through that process. Where would 120 be? And should be pretty confident with the fact that that is a quadrant 2 angle, somewhere up there, give or take. Probably a little closer to that y-axis. But that would be 120 degrees. Good. A quarter of a rotation around, everyone, would be 90 degrees. Again, I asked you to kind of visualize that one before. So terminal side would be on the positive y-axis up here. Again, please make sure you include the rotation. All right, so half, third, a quarter around. Again, two things. We're assuming all these are counterclockwise at this point. So in this case, the fraction of the rotation now allows us to put a numerical value on its measurement. That looks great. A sixth of a rotation around. I'm hoping everyone is okay with me saying it's 60 degrees. And again, it doesn't have to be perfect, but essentially 60 degrees would look something like this. Let's see if I can get that in there. There we go. So there's 60 degrees. An eighth of a rotation around, an eighth of 360 would happen to be 45 degrees. Again, you're going to really need to know these numbers, guys, so please start thinking about them. Start seeing them in action, if you would. There's 45 degrees right there, splitting that first quadrant. So 45 degrees right there. And then a twelfth of a rotation around is 30 degrees. And so let's go ahead and throw 30 degrees in there and see what it would look like. And from there to there, give or take, a little closer to the x-axis as opposed to the y-axis. So if you remember from geometry, of course, 45, 45, 90 triangles and 30, 60, 90 triangles, we'll definitely be getting into those. There is just a lot that you work with the 30s, the 45s, the 60s, and all the multiples of those. So start getting familiar with those numbers, please, and again, see it, definitely visualize where those angles are as you go through. Okay, so we have now fractions of rotations, degree measurements, and sketches that match. Looking great. I'm going to move to my next page right here, and let's do just a few examples here, just again starting to work through the process a little bit, and really starting putting directions and the amount of rotation with a numerical measurement. In this case, the unit would be degrees. We're going to kind of put that on its head in just a little bit here. We're going to change it up and do a different unit of measurement, probably over the next couple days. But let's start this right here. So it's to determine the degree measurement of each angle. Notice I've got the fraction of the rotation and I have the direction of the rotation. Based on those two things, should be able to give me a numerical value. And also, everybody, you should be able to visualize that terminal side. So let's give this a try. And, the first one's always the hardest, just to kind of get a feeling for it. But here's what I would do. Just right away, I would say, all right, well, it's 2/3 of a rotation. And you do this a lot in your science classes, and you're actually going to be doing this a lot in trigonometry. But essentially, I want to change from the idea of a rotation to the unit of degrees. Well, what do I know to be the case here? I know that 360 degrees is one rotation. This is what is called dimensional analysis. And so you can see, and again, if you don't need to kind of go through all this hoopla that I'm doing up here, that's perfectly fine. But essentially, I want to go from rotations to degrees. And this fraction, where with 360 degrees is one rotation, allows us to do that nicely because rotations are going to cancel. And then essentially, I get 2/3 times 360. And so if you have an opportunity there, grab that calculator and take 2/3, multiply it by 360. And 2/3 of 360 should be 240 degrees. Now here's where we do have to be a touch careful, everyone. Remember, in trigonometry, direction does matter. So a clockwise rotation is very different than a counterclockwise rotation. The terminal side would be in a totally different place based on this word right here. So, a clockwise rotation would be negative. And so that would be our answer right there. So equals, and then in this case, negative 240 degrees. Okay, can you visualize negative 240 degrees? Which quadrant would it be in? Think about that for a moment. And again, try to work through some of this. Negative 240 would be up in quadrant 2, as a matter of fact, up in quadrant 2. Probably a little closer to the y-axis than the x-axis. Okay, let's go through letter B, so 1 1/4. And so here's how we want to play this out right here. So I've got one rotation. That rotation is 360 degrees, plus another quarter of a rotation, so a quarter of 360 degrees. Again, just kind of shortchanging what we did a little bit on part A, but essentially we saw it to go from rotations to degrees. I just really multiplied by 360 degrees. And so in this case, one rotation, that rotation's 360, plus another quarter of 360. And if you end up pulling this off here, it looks like it would be 450 degrees. And the question, of course, is it positive? Is it negative? And it definitely does matter. It looks to be positive, so that would be our answer. 450 degrees would be 1 1/4 counterclockwise rotation. So can you visualize that, going around and then another quarter of the way and then putting your terminal side? Okay, good. Let's see, 7/8 of a counterclockwise rotation. So 7/8 of a rotation means 7/8 of 360 degrees. So I would just basically take that, 7/8, and multiply it by 360. And if you do that, then you can grab your calculator there. I end up getting about 315, well not about, but exactly 315. And again, you have to make the determination, is it positive or is it negative? And in this case, it is a positive angle measurement. 7/8 counterclockwise would be 315 degrees. Think about that for a moment. Which quadrant would it be in? And in this case, if you thought about 315 degrees or going 7/8 counterclockwise, it should be in quadrant 4. We're going to see that 315 pop up, so visualize that one. Next one here, letter D, 3 2/5 clockwise rotation. So 3 rotations, each one of those is 360 degrees. So 3 times 360. And then another 2/5 after that, so 2/5 of a clockwise rotation, so 2/5 of 360 degrees, and that to me is the easiest way to kind of pull that off. And if you take 3 times 360 and then add the 2/5 of 360, I end up getting 1224 on that. Again, don't stop there though. Think about that. That's the amount of the rotation translating into a degree measurement. But we also want the direction to translate into the degree measurement as well. 2 parts to it. Clockwise, everybody, is negative. So envision that going around once, twice, thrice, and then another 2/5. And you can see you're starting to get into some pretty large numbers there, 1224 in the negative direction. Okay, good. Let's maybe just reverse course a little bit here, and I'll kind of leave this to your discretion. It says, determine the rotation of the angle for each degree measurement. Write your answers as reduced fractions or mixed numbers when appropriate. Okay, so I'm going to have to reduce some fractions here. We're going to go over part A, and then we can kind of work through some of these. But basically, here's the concept with this one. I'm at 40 degrees, and what I'm looking for here is actually to reverse it, to go from degrees to rotations. Well, what do I know about degrees and rotations using that idea of dimensional analysis, everybody? Well, I know for a fact that one rotation is 360 degrees. And so you can kind of see how this works out. Again, we're going to do a lot of this, changing the units without changing the value. In this case, going from degrees to rotations. And degrees would cancel, so I'm going to X those on out there. And we get 40 times 1 over 360. So you can write this or not write this, it's up to you, but basically this would be 40 3/60ths of a rotation. The degrees canceled and we got that. And again, as it says in the instructions there, write your answers as reduced fractions when appropriate. So you could think about this as what is 40 over 360, and just to expedite this along, should be 1/9. So 1/9 of a rotation, and we have to be careful when we talk about an angle measurement. Really, it comes from 2 things: the amount of the rotation and the direction of the rotation. So at this point, this answer is not complete. So this tells me the amount of the rotation, 1/9 of the way around, but I need to go direction too. So counterclockwise for a positive angle measurement. So please make sure you have both components in place. Otherwise, again, it is incomplete. 1/9 going around counterclockwise is quite a bit different than 1/9 going around clockwise. Those terminal sides would be in 2 entirely different spots. Okay, so match up the terminal side with the angle measurement and the rotation. Put it all together, everybody. Okay, so let's go into the next one here, negative 54 degrees. And again, what I would do is just change the units, change it to rotations there, so 360. Again, those are going to cancel. And I basically get 54 over the 360. So it's 54 3/60ths of a rotation. Now, if it's okay with you, what I'm going to ask you to do is take a moment and reduce this fraction. If you can kind of pause that video for me, that would be great. But I will leave that to your discretion. When I actually put this together and reduce that fraction, 54 over 360 happens to be 3/20ths. So that would be the fraction of the rotation around. So it's 3/20ths of a rotation. And in this particular case, clockwise rotation. Negative angle measurement, clockwise rotation, of course. Okay, let's do at least C and D here, and then we'll continue to move forward with this. So here's where we have to be a little careful. And we could think about this a couple different ways, but same idea. I would do 540 times the 1 rotation over 360. 540 times 1 is 540. So this, and again, it does say instead of an improper fraction there, instead of saying it's 5/40th 3/60ths of a rotation, let's think about that maybe in terms of a mixed number. So you can grab your calculator if you'd like. There's so many different ways and perspectives on this one. But I hope everybody would be okay if you did 540 divided by 360, you would end up getting 1.5. So what that means, really 1.5, is 1 rotation for the 360. And then you would have another 180 degrees after that, and 180 out of 360 is a half a rotation. So the way I'm envisioning this is it's 1.5 rotation, or yes, 1.5 rotations in a counterclockwise direction. So we have 1.5 counterclockwise for letter C. Alrighty, excellent. So the last one here is the 1200. And so again, we're starting to get some fairly large numbers on these. And in this case, it's in the negative direction there, so clockwise rotation when we get it. One more time, everybody. I'll kind of do it like this. 1 rotation, 360 degrees. Degrees are going to cancel. And I end up getting really 1200 3/60ths of a rotation. But to me, that's not the best way to describe this. So what I'll ask you to do is, at this stage, is pick up your calculator. And you can kind of work through this a variety of ways. But basically, I would say something along these lines right here is, let's do 1200 divided by 360. And as a matter of fact, I'll do this with you, just maybe kind of walk you through what I'm thinking with this. But if you can pull this off on your own, that's great. So the way I'm seeing it is 1200 divided by 360. Let's see how many rotations we're talking about. And it looks like from this we can probably decipher what it is. It's 3 full rotations and then a fraction of a rotation described by this decimal right here. If you understand what that decimal is, that's great. I mean, it seems to be 3 1/3, and I think we can kind of go forward from that piece. If we didn't understand this, then maybe I can kind of figure out a couple ways to do this. So if you have it, you can just write this in and then move forward here. But basically, I would say, okay, well, I know it's 3 rotations around. And so maybe I would go back and say something like, okay, well, 360 times 3 is 1080. So 1080 would be 3 full rotations around. But then to get the 1200, let's see what's left over. So 1200 minus 1080 is another 120. Oh, okay. So it was 3 full rotations, and then I had 120 degrees left over out of the next 360. And so 120 over 360 is 1/3. So again, not sure how you want to go ahead and play that out there, but essentially what I would say is it's 3 1/3 rotations, and because it is negative, it is clockwise. Okay, so we had 2 counterclockwise, and let me throw in just a rotation aspect right there, and 2 clockwise rotations. Okay, direction and the amount lead into the angle measurement. Okay, let's get into the last piece here. So example 3 is now just starting to visualize. Really, I should be able to give you an angle measurement in degrees. You should be able to see it on the coordinate plane. That is a huge aspect of what we're going to be working on. So please start that process here today with me. So I guess what I'd ask you to do almost is pause the video and see if you can draw all 8 of those in standard position. Okay, so all 8, work through piece by piece, and then come on back and then see how you did. Okay, well, let's check it out here. So again, just kind of working through. I would standard position right there. So initial side is on the positive x-axis, negative 60 degrees, so it's going to be a clockwise rotation. 60 degrees seems to be coming down here, give or take, and that would be negative 60 degrees. So probably a little closer to the y-axis than the x-axis. Again, no protractors today. We'll get into all that stuff a little later. Just need you to be able to starting to visualize them in general terms, but being able to see where you think they would be. All right, next one, 210 degrees. So 210, everybody. 180 we know would take us here, and then 180, and then another 30 to get us down there. So 210 is a quadrant 3 angle. Again, a little closer to the x-axis than the y-axis. Okay, counterclockwise direction on that one. Letter C, negative 135. So this is going to be a clockwise direction. And 135, again, just kind of working this way. This would be 90 degrees if I made it to this axis right here. And in another 45 degrees. So I'm seeing it as splitting the third quadrant right there, right in the middle, just like that. We'll see a lot with the multiples of 45, so please understand that 135 right there. In this case, clockwise, so the negative angle giving us clockwise direction. Okay, 270. Again, just kind of working our way around counterclockwise. There's 90, there's 180. There it is, 270. I think we're on the negative y-axis when all's said and done. That's it right there. That's 270 degrees. Again, must be able to visualize these. So if I throw 315 degrees at you, you can see that terminal side. You know the quadrant, and you can basically ballpark where that terminal side is in the fourth quadrant, which, as a matter of fact, should split the fourth quadrant, kind of like that. Please don't forget you must include the rotation in order to make it complete. And we'll talk about this probably on the next lesson, but really, theoretically, there are an infinite number of ways to get from here to here. You need to indicate based on the measurement. So 315, by the way, also happens to be another multiple of 45 degrees, as is 225. And 225 happens to be right there as a terminal side. So, and by the way, just notice your answers from C and F, they happen to be the exact same position. So you can have the terminal side in the same spot, but two different ways to get there, and hence two different angle measurements as a result. Okay, so this is 225 degrees. This is negative 135 degrees. Two different angle measurements. Be very clear on that piece. 240, everybody. 240 is also quadrant 3, a little closer to that y-axis, something like that. And in 405, we haven't kind of seen more than one rotation around, but we can definitely draw it in. One rotation would be 360, and then it looks like we would need another 45 degrees. So I'm seeing the terminal side ending up here, but again, we have to be careful. This is 405 degrees. That's the key. So one full rotation around, and then another one to 45 degrees. So 405. Okay, now two huge questions, I think, before we round this out here. So please highlight those and understand these two pieces. If you really do, it allows us to take many steps forward here. So the first is this. What is the interval for possible angle measurements? Now, if you think about this for a moment, and I kind of go back to letter H for just a second, is there really any endpoint in sight in terms of theoretically rotating around? Can I rotate a terminal side again and again and again and again in a counterclockwise direction? Sure, I can just keep going and going and going infinitely. Also, if you think about it, in the other direction, theoretically, can I rotate a terminal side clockwise again and again and again and again and again infinitely? And the answer would be yes. So as a result here, because I can do an infinite number of rotations counterclockwise and an infinite number of rotations clockwise, then the interval really for possible angle measurements is this. This is what's kind of fascinating about it. So anywhere from negative infinity to infinity. So in reality, basically, an angle measurement can be any real number. In fact, I'm just going to write that off to the side. And we'll see that. And that is a huge piece for us. I don't think you've ever kind of really dealt with angles in that capacity before. But an angle measurement can be any real number. Okay, good. And then one more piece that really comes into play nicely here. If we were to track a point on the terminal side of an angle as it rotated off the initial side, what type of path would it make? Now, you don't have to write this on your paper if you don't want to, but think about it this way. Here's the initial side right here. I'm just going to put a terminal side up here, something like that. And I'm going to put a little tracer on a point. So that terminal side, it rotated off the initial side. We'll just call it from here to here. And if I really just kind of track that one point, and I put a little tracer on it, and I track it, what kind of path would it make from here to here? And if you were to follow this around, you would kind of see it just like this. And it shouldn't come as a great shock, as all of what we talked about is intertwined. But you should see that it forms a circular path. And we're going to talk a lot about that coming up. Okay, so sometimes the trig functions are called circular functions for that very reason. And so what we're going to do is really start to take a look at the concept of a point moving around the circle and its connection to the angle right in here. That is a huge, huge piece for us. So again, this forming a circular path as this angle changes right here. And those two are intertwined in a variety of ways. Okay, so some really good stuff. We'll obviously continue the discussion on the next one and the next one after that. But I think we laid a nice foundation here today. And please let me know if you have any questions as you work through some of the problems. And as always, thank you very much for listening.